on entering astrophotography without fear. They have a program that I know I've mentioned to the group before called the Astrophotography Conference. It's October 7th to the 10th. It's $300. It's a 4-day workshop where you come in on Thursday and you leave on a Sunday morning before the afternoon, usually up around Tupper Lake. And it's kind of geared at hands-on experience for people that are interested in astrophotography, sort of regardless of which skill level you're at, because they cover, they have different lectures during the daytime, and then at night they actually go out to the observatory. You can set up your own scope, or you can use other people's scopes, get some hands-on experience, and get some help from people that already know what they're doing or have seen some of the problems that you're having, etc. And if the skies are nice and dark up there in Tupper Lake, it's kind of the darkest areas in the Northeast. So if we get some imaging one night, then we actually go through post-processing in some of the lectures as well. So you can actually work on post-processing your data and get some hands-on experience with things like PixInsight and that kind of stuff. If you haven't had it before, or, you know, there's steep learning curves for all of that. So there's really nobody that knows everything, but collectively the community of people that show up there are always friendly and everybody shares. And I found it very helpful the last couple of years that I've gone. So you wanted me to share that with you since it is in person again this year and it got canceled last year. So you can check it out, the AdirondacSkyCenter.org. They do have a way to sign up online and pay online if you'd like to attend it this year.
Stick that flyer up in the events section of the Slack channel. Cool. All right. And with that, it looks like I'm only over by a minute, so that's pretty good tonight. We'll bring to a close the July meeting of Mid-Hudson Astronomical Association and pass the session over to Alex to introduce our speaker.
Hi, so I want to introduce everybody to Alex Howe. It's nice to see you, Alex. Finally, get to see your face. And he's going to be giving a presentation titled SuperEarths to Super Jupiters, Understanding the Atmospheres of Exoplanets. So he sent me his CV, which is 2.5 pages. I'm going to focus on the first page. He's presently at NASA postdoctoral program at Goddard since 2019. He had a previous position of a postdoctoral research fellow at the University of Michigan for 3 years. His research interests are exoplanet and brown dwarf atmospheres and spectral modeling, exoplanet and brown dwarf spectroscopy and retrieval, and mass loss processes for exoplanets. Really interesting to me. He went to graduate school at Princeton University in the Department of Astrophysical Sciences. He got his BS from Ohio Wesleyan University in the Department of Physics and Astronomy as well. He has spoken at many conferences, given many talks, publications, really experienced at what he's been doing for quite a while. So I'm glad to introduce you, Alex. Why don't you go right ahead?
Okay, thank you. And I should be able to share my screen.
Yep, it's coming.
All right. Okay, had to make room on my screen there. So thank you for inviting me to speak. I want to talk about 2 ongoing research projects that I'm working on here at Goddard. And as Jack said, just put questions in the chat. Since there's 2 projects, I'll check the chat halfway through and we can look at any questions then. And before I start, I just want to say congratulations to Blue Origin. Now all we need to do is convince Elon Musk to write his own rocket and we'll have the trifecta. So exoplanets are still a very young field in astronomy, even coming up on 30 years. And it's a very fast moving field. Information from even 10 years ago is often out of date now because we understand things so differently. We've discovered about 4,000 planets, and this is a chart of discoveries over time, broken down by discovery method. Of course, the largest number are transiting planets in the green, and you can see Kepler, K2, and TESS, the three major transiting planet missions that NASA has run. But you can also see radial velocity in the pink, and that's continuing to improve and will continue to improve along with various other methods like astrometry from Gaia. And next generation observatories may discover as many as 100,000 planets in the next 10 years. And there are a lot of things we can study just from the discovery statistics, like dynamics and formation. However, my field of study is atmospheres. So why study atmospheres? Well, to start with, they're easier to observe than surfaces. And when you discover a new astronomical object, the first thing you do is take a spectrum. And you can get a lot of information from spectrum. You get chemical composition of the atmosphere, and that gives clues to the formation, insights into the climate of the planet that can be applied to some extent even on Earth. Understanding more about climate in general is always helpful. And also, there are planets out there that look like Earth did 3 billion years ago, or will look 3 billion years from now. So that can tell us about Earth's history. And of course, there's the number one question everyone wants to know. Could any of the planets we've discovered harbor life? Now, unfortunately, planets are hard. Victoria Meadows likes to show this slide in her talks, showing all the factors that affect habitability, properties of the star, of the entire planetary system, and all kinds of things about the planet, the interior, atmosphere, surface, orbit. And all of this matters for habitability. Some of these things are very hard to observe, plate tectonics, magnetic fields, that kind of thing. We won't understand all of it for a long time, if ever. But luckily, we just need to understand enough of it to make sense of what we're seeing. To make sense of what we're seeing in the atmosphere and interpret whether it's related to life, because even oxygen can come from non-biological sources. You just have water molecules broken apart by UV radiation, and the hydrogen escapes to space, and it leaves free oxygen behind. So if we want to understand habitability, we need to try to chip away at all this stuff. And the first thing we need to do is find the right kind of planet. And there are many kinds of exoplanets that we can see just from the discoveries. This is another plot of all of the known planets. This is complete as of last week, with known masses, of course. So this is mass versus orbital period. And again, you can see the discovery methods. Transiting planets are mostly closer in than radial velocity planets. And I'm going to draw in some planet populations on this graph. First, clear the text away. And I'll draw in the solar system planets, all 8 of them. You can include Pluto if you want, but it'll be off the bottom of the screen. Then this line up top, this is 80 Jupiter masses, which is the hydrogen burning limit. So everything above this line will be a star. This line is at 13 Jupiter masses, which is the deuterium burning limit. So everything above this line will be a brown dwarf. And you see there are a few objects in this range, and that's just because it's hard to get exact measurements of these, exact mass measurements of these objects. So these are things that we're not quite sure whether they're planets or brown dwarfs. Then moving down, here's Jupiter's mass, here's Neptune, and here's Earth. And we can see particular clusters on the chart, like the cold Jupiters, which are just planets that are similar to Jupiter. The hot Jupiters, which were the first planets to be discovered around main sequence stars. And they're like Jupiter, but orbit very close to their stars. In between, we have the warm Jupiters. And this is an interesting case because we see more of them than we expect. We expect to see some planets in this region, but mostly we expect them to be migrating through it to become hot Jupiters. And that we see so many of them is a puzzle that we're still trying to figure out. Then below the Jupiters, we have this region, which is called the sub-Saturn desert. And these are planets in between the mass of Saturn and Neptune. There are a lot fewer of them, but we're not sure if this is real or if it's just a statistical artifact. So that's another puzzle we're looking into. And below that, you have this blob, which is a type of planet known as SuperEarths. No, not that kind of super Earth. This kind of super Earth. This is an artist's rendition of Kepler 22b, the first quote unquote potentially habitable super Earth found by the Kepler Space Telescope, except not this kind of super Earth either. We now know that a planet this large will have a deep hydrogen atmosphere like Neptune and will not be very Earth-like. Instead, we want this kind of super Earth. This is an artist's rendition of TRAPPIST-1e from TRAPPIST-1, the famous system of 7 planets that has everybody excited the past few years. We don't know if it looks like this. We don't know if it has water, but it is almost certainly rocky, and it is larger than Earth, so we call it a super Earth. And to understand the distinction between these two groups, we need to take a closer look at that lower blob on the graph. So I have a slightly different version of that graph here. Note that this time we're looking at radius and period rather than mass and period. So these are just the transiting planets. And the outer edge in terms of orbital period is a lot shorter. And we can still see some of the populations on the graph. So here's Earth and Venus. They're the only solar system planets that fit. There's the hot Jupiters, Jupiter's radius, and Neptune and Earth. And of course, you can still see what we previously called the blob of super-Earths. But if you look closely, there's a region right through here that doesn't seem to have as many planets. It's subtle, but if you do the statistics, you find out that that gap is real. And it divides this population in two. Above the line are what we call mini Neptunes, which obviously are like Neptune, but smaller. And below the line are super Earths, which are rocky planets like Earth, but bigger. And there's one more area you need to know about. That's this one. This is the Neptunian desert, a region close in towards the star where Neptune-sized planets are almost completely absent. And this feature is also real. And this is caused by intense ultraviolet radiation from the star evaporating away the atmosphere. So are any of these planets habitable? Or are they hydrogen, lifeless rocks, water worlds, Venus-like, frozen? To figure that out, we need to look at their atmospheres. And the first project I'm working on is studying the loss of hydrogen atmospheres that can turn these mini Neptunes into super Earths. Now, how do I study these planets? Well, I'm a theorist. So that means the first thing I do is build a virtual planet in a computer. Okay, to build a virtual planet, you start with an iron core. And on top of that, you put a rocky mantle. And I should note that In the literature, you will often see the entire solid part of the planet referred to as the core, not just the iron part. That's one of the areas where the terminology is ambiguous. Then on top of the rock, this is where we have to make a choice. There may be a water ice mantle like you see on Europa and other outer solar system satellites. And this is important because what the surface is made of determines what the atmosphere is made of, at least the secondary atmosphere, if the hydrogen and helium are stripped away. If the surface is rocky, the atmosphere will be mostly CO2, like on Venus. But if it's a water world and the water is deep enough that volcanic activity doesn't reach the surface through the layer of ice, then the atmosphere will be mostly water vapor. Now, looking at transiting planets, which are all warm and close to their stars, we think this water mantle is not there. For planets out beyond the ice line, it would be different. Now, on top of this rock and iron core, we add an atmosphere. And by default, we're looking at a hydrogen-helium atmosphere. That has different layers too. There's a convective layer and a radiative layer, which has to be figured into the computer program. And once you have your planet, you have to put it in its environment. Planets orbit stars, so they will be exposed to incoming starlight. They will radiate away infrared light. And they're also exposed to ultraviolet light from their stars. And this causes a process called photoevaporation, where the ultraviolet light causes the atmosphere to blow away into space. And one of the things I study is the loss of hydrogen atmospheres from low mass planets. And these mass loss processes also tie into the two models of rocky planet formation. And looking at them can give us clues to the formation of these planets. So I'll give a quick overview of planet formation. There are two theories. The first one is called planetesimal accretion. And in planetesimal accretion, you start with a disk of gas and dust surrounding a star. And some of the dust condenses into planetesimals. But intense ultraviolet radiation from the young star evaporates away the gas and ice from the disk, leaving only rock and iron. These planetesimals collide to form Mars-ish sized protoplanets. And over tens of millions of years, those protoplanets collide to form a final planet like Earth or Venus. The planet forms dry, and water is delivered by comets. The second model is a more recent one called Pebble accretion. And in Pebble accretion, you start with the same disk of gas and dust, but planetesimals form more quickly, and they sweep up pebbles from the disk. Pebbles are anything from actual pebbles to meter-sized objects. And there are certain gravitational instabilities around large planetesimals that will sweep them up much more quickly, we think. And that will form planets faster. And because the disk is still around, the planet forms wet by acquiring water from the disk. And because the disk is still around, even after it evaporates, the planet will retain about 2% hydrogen by mass, even for Earth-sized planets. Contrary to popular belief, Earth is massive enough to retain a hydrogen atmosphere, just not one as deep as the gas giants. Could this be the origin of mini Neptunes? 2% is actually about right for a wide range of the mini Neptunes we see out there. And there's a tension between these two theories. Planetesimal accretion is the standard model. It's what people came up with long ago to some extent. It's what has been sort of the standard for decades. And it makes sense for Earth and the other solar system planets and super-Earths. It explains the formation of the moon because you need another Mars-sized planet to crash into the early Earth to form the moon. And most tellingly, the isotope ratios in our oceans match those found in comets, not those found in the asteroid belt or on Mars. And that suggests that Earth's water was delivered from the outer solar system. But if all that's true, where do mini Neptunes come from? They could migrate in from the outer solar system, but like I said, they don't seem to have enough water. We can observe the distribution of masses and radii and conclude that they're probably mostly dry. Now, Pebble accretion makes more sense for exoplanets. It explains those mini Neptunes. They just get their hydrogen from the disk. It also explains why we see so many compact systems with lots of planets like TRAPPIST-1. Because of friction with the disk, you don't have as many collisions of protoplanets, and so they can form in nice, neat circular orbits close together. But if that's true, why doesn't Earth have a hydrogen atmosphere? And the working theory is that hydrogen could have evaporated later. Now, it also doesn't explain the moon forming impact. And that's why we're leaning towards it's a combination of both. Hybrid models of planetesimal accretion plus Pebble accretion are in development. But I'm looking less at that and more at evaporating the atmospheres once they form. And to evaporate an atmosphere, especially a hydrogen atmosphere, there are many processes that can be involved. Some molecules can simply by chance have enough kinetic energy to escape the planet's gravity well. This is called Jean's escape. If the atmosphere is very hot and fluffy, you can just have outflowing winds as it blows off into space. You can have solar wind ablation, where protons from the solar wind knock molecules out of the atmosphere. Impact erosion, because giant impacts will certainly blow away some of the atmosphere. And then you have this stuff. This is photoevaporation, where ultraviolet photons strike the atmosphere. They don't actually eject particles directly. It's more that they heat the atmosphere to drive these winds, but this illustrates what's going on at the micro level. And also they're ultraviolet photons, not blue and red. This just represents the frequency. But what most people have been studying for evaporation of atmospheres is this here, photoionization, where an ultraviolet photon hits the atmosphere, breaks apart a hydrogen atom into a proton and an electron, and that goes into heating the atmosphere and driving the outflow. And this is nice, but a couple of years ago, working with Michael Meyer and Fred Adams at the University of Michigan, I realized this was missing a piece of the puzzle, which is this piece. This is photodissociation, where a slightly longer wavelength ultraviolet photon breaks apart a hydrogen molecule into two atoms without ionizing it. And this has been known in solar system science going back to the 60s, but it hadn't really been addressed for exoplanets. Probably in part because exoplanet people came from the stellar community and solar system science people came from the planetary science community, which is not the same thing. And we wrote a paper that came out last year examining this process for exoplanets. And to do this, the first step is you need to model planets with different compositions so you can compare them. And this is actually something I did with Adam Burrows and Wesley Verne at Princeton in 2014. In this case, we took pretty much all the planets that had known masses and radii at the time. There were a lot fewer of them. And plotted them on a grid of theoretical models. And these are models of planets at a given temperature, where the vertical lines are lines of constant core mass, and the horizontal lines are lines of constant atmosphere mass. And if you know a planet's mass and radius, you can estimate both the core mass and the atmosphere mass from this plot. And I'd like to call your attention to this area here, where you can see a little bit of a gap. And I'll draw it in so it's clearer. And this is right where that gap between super-Earths and mini Neptunes is. And we did notice this at the time, but we didn't have good enough statistics to tell if it was real or if it was just an artifact. There weren't enough planets known at the time to really pin down what was going on here. That would have to wait for B.J. Fulton and the California Kepler survey in 2017, which got many more masses and radii, very precise masses and radii for planets. And in fact, you can see it with just radii and orbital period. This gap where there are still planets, but there are fewer of them. And this gap is called the evaporation valley, or sometimes just the Fulton gap. And it's caused by evaporation of atmospheres, moving planets from the mini Neptune blob up here to the super-Earth blob down here. And this happens because the last little bit of atmosphere adds a lot to the radius, and it evaporates away very quickly, so planets move very quickly through this valley from one side to the other. Now, going back to the planet model, we can build a computer model of its internal structure. So this is from that same paper. And you can see density and pressure of a typical mini Neptune versus radius. And this is the iron core, this is the rocky mantle, and this is the hydrogen envelope. And you can see even the blue line, which is 0.2% hydrogen by mass, it adds 1/10 of an Earth radius. And this is enough to show up in a good quality transit survey. And 0.2% is going to evaporate very fast. So this is where it crosses through that valley. Now, this is not an evaporation model, it's just a structure model. We did evaporation models in our next paper the following year. And this is simply building a young planet that is hotter, letting it cool off over time and letting the atmosphere evaporate, exposed to ultraviolet light from the star. And you can see the radius decreases over time, and the dotted and dashed lines are different amounts of mass loss. And you can start with a larger than Neptune planet also works. Smaller than Neptune planet, this blue line is where Kepler 22b might be, for example. And this culminated last year in my paper with Michael Meyer and Fred Adams, where we modeled these processes with the new photo dissociation for the early Earth. Because if Pebble accretion is correct, the early Earth would have a hydrogen atmosphere that needs to be evaporated. And we looked at various mass loss processes and how much mass they would remove. 2% of Earth's mass is equal to 23,000 atmospheres, which is a lot of mass. For comparison, the oceans are only 300 atmospheres. And we were not able to remove that much hydrogen. You can calculate how much ultraviolet radiation the sun puts out over its entire history. It's not enough to evaporate that much hydrogen. Now, in the table, you see photo dissociation is very small. That's because we kind of assumed it was the same efficiency as ionization. Ionization is usually assumed to be about 10% efficient, but there are some studies that suggest dissociation may be higher, as high as 25% efficient. So you would actually want to multiply this total by 2.5 rather than just the dissociation, because photoionization and dissociation occur in close to the same wavelength range. But even if you do that, you still don't have enough mass loss to strip that much hydrogen. The moon forming impact won't work either. It's not symmetrical enough. It will blow away the atmosphere from one side of the planet, but leave the other side on fire, but intact. So we think that the only thing that really works to remove that much hydrogen is a hybrid model. If planetesimal accretion happens, then you also still need to accrete 10% or so of Earth's mass as large impactors to strip away the hydrogen that it would gain. So the next step for this project, which we're lining up now, is to extend this photo dissociation model to the full population of super-Earths and mini Neptunes. And we want to start with a planet formation model. There are several of them floating around. Plug that into our mass loss model and see if we can recreate the evaporation valley and the Neptunian desert. And for specific objects, we want to try to predict atmospheric properties of James Webb Space Telescope targets. Obviously, that's a very high interest. And by modeling mass loss, we may be able to predict metallicity, chemical compositions, and with the help of some cloud modeling people, what we expect to see in terms of clouds. And that's also something James Webb can look at. Maybe would prefer not to, as I'll explain in the next section, but we can get information from clouds directly, even when they're obscuring the rest of the atmosphere. And we also want to look at M-dwarfs. M-dwarfs produce a lot more ultraviolet light versus visible light. And that means M-dwarf planets should show different patterns of photoevaporation versus impact erosion. So we want to extend our mass loss model with new measurements of M-dwarf ultraviolet output and flare rates. My colleague Michelle Silverstein here at Goddard is doing some of that. And hopefully precise measurements of the M-dwarf planet population that we should get in the next decade will yield new insights into the mass loss processes and formation processes that are happening with these planets. And that's the first half of the talk. So I'm going to take a minute to view the chat if I can.
I don't actually see any questions in the chat right now.
Okay. Then I will continue with the second half.
Perfect.
So this is all about the history of atmospheres and their formation. The other question that you probably want to ask is, what are atmospheres made of today? And for that, we use spectroscopy. In 1925, the famous astronomer Cecilia Payne-Gaposchkin used stellar spectral lines to determine that stars are mostly made of hydrogen, which was a big surprise at the time. In principle, we should be able to do the same for planetary atmospheres. But there's a problem. Planetary atmospheres are made of molecules, while stellar atmospheres are made of atoms, and molecules are way more complicated. And there's another problem. Planets are really, really faint. So they're a lot harder to observe than stars. And another problem, clouds. Clouds everywhere. They give us a lot of trouble. Now, a partial solution to that is to look at a type of planet called super Jupiters, and also hot Jupiters. And this actually is to scale. This is roughly the scale of a hot Jupiter and its host star in both size and distance. So that's how close they orbit. And you may be thinking, hang on, what about super-Earths? Well, I have looked at super-Earths and they are hard. This was my very first paper with Adam Burrows at Princeton. And we were looking at what at the time was called a super-Earth GJ1214b. This was so long ago that we didn't fully understand the distinction between super-Earths and mini-Neptunes yet. And we now know that this planet is a mini-Neptune with a deep hydrogen atmosphere. But at the time, what we knew is that it had, it's kind of hard to see behind the models, but there are some data points here that look like they could be a water absorption feature. And we fit some spectra with water. The blue line, the cyan line is a water-based spectrum that did seem to fit that, but none of them fit all that well. And it turned out this was because there was no water feature. 2 years later, Laura Kreidberg went back with the Hubble Space Telescope and took a better spectrum, and it was completely flat. Water feature completely disappeared. And we think that's because the clouds were blocking the light from the lower atmosphere. So clouds everywhere. And this is a problem that happens with most of the mini Neptunes we look at. We are just now starting to understand how to get good spectra of mini Neptunes. And we will need next generation telescopes and new techniques to understand super Earths and regular Earths. Even James Webb, we're putting a lot of hours into the very nearest planet, Proxima Centauri b, to get anything out of a super Earth. We really need the 30-meter telescope, Giant Magellan telescope, extremely large telescopes. But in the meantime, studying giant planets helps us to refine our techniques and learn more about atmospheres in general. Now, there are many ways we can take spectra of planets. You have transits where the planet passes in front of the star, and some of the starlight passes through the planet's atmosphere and leaves a chemical signature. You can have what we call secondary eclipse when the planet goes behind the star. And this is useful in the infrared, especially for very warm planets, because warm planets emit their own infrared light. And when they go behind the star, that light is subtracted from the total spectrum. And you can also have a phase curve as the planet goes around its orbit, and you see varying amounts of day side and night side. Now, this is for transiting planets, which is the majority of planets that have currently been discovered. It also works for non-transiting planets. You can take a phase curve. But more interestingly, we also have directly imaged planets. And this is where the super Jupiters come in. Super Jupiters are planets that are more massive than Jupiter. And that means when they form, they stay hot for longer. And if they're far from their stars, they can be imaged directly, and we can take a spectrum directly in the infrared. And the same is true of brown dwarfs, which share many similarities. They're a little more massive, but otherwise they look pretty much the same in a telescope anyway. And my project is actually currently looking at the atmospheres of brown dwarfs. But like I said, there's a lot of overlap, and you can apply the same techniques. And we want to study the atmospheres of these distant companions because they, again, give us clues to planet formation. Much like rocky planets, there are two formation models for giant planets. And we have a better handle on when each of these occur. Both of them are correct in specific circumstances. For close-in giant planets, and close-in this context includes Jupiter, you have icy planetesimals out beyond the ice line where they don't evaporate, which form a 10-ish Earth mass core. Because the ice doesn't evaporate, there's much more mass to work with. Once the core hits 10 Earth masses, it's big enough to sweep up all the gas in its orbit, and grow into a gas giant. This explains Jupiter fairly well. It explains Saturn fairly well. It doesn't explain much that's larger than Jupiter or Saturn. Once these planets form in a Jupiter-like orbit, they may stay where they are. They may migrate inward toward the star and become hot Jupiters. And they may also be scattered to large distances by interactions with other planets. Now, for planets forming way outside the disk, there's not really a disk to work with. And we expect those objects formed by direct gravitational collapse, much like stars do. And in fact, if we look at the brown dwarfs and super Jupiters, they match the extreme low mass end of the stellar mass function. And this process makes brown dwarfs and super Jupiters from about 5 Jupiter masses up. But there's some overlap between the two processes. And I should note that Michael Meyer at Michigan is studying how much that overlap is and exactly where it happens. Also, direct gravitational collapse forms hotter planets. There's more gravitational energy going into them, but after 100 million years or so, they cool to about the same level. So that only helps you characterize young planets. For older planets, you can tell where it formed by its atmospheric chemistry. Here's a simple illustration of what's going on. Basically, in the inner part of the disk, all of the volatiles, water, methane, carbon dioxide, that kind of thing, are in gas phase. And anything in gas phase winds up in the atmosphere. And because those all are just coming from the disk, you expect the atmosphere to have similar elemental abundances to the host star. And we're specifically looking at the carbon to oxygen ratio. Because as you move outward beyond the ice line, water condenses into ice and rains out into the core. This means the atmosphere is depleted in water and has much less oxygen, so we expect a higher C to O ratio here. And further out beyond the edge of the disk, everything rains out equally, so we expect the C to O ratio to be back to where the host star is again. We don't really worry about close-in objects because those probably aren't going to be scattered from 0.1 AU all the way out to 100 AU. But objects at 5 AU might. And if we see objects out here, we want to distinguish if they formed there or if they migrated there. Now, how do we find these chemical abundances? We use spectroscopic retrieval. And this is a very powerful tool. It's used in stellar astrophysics as well. A lot of people are putting a lot of work into this for planets. And this is a basic illustration of how it works. You start with some observations of a planet spectrum. It's kind of hard to see, but there's a black line under here, and that's the observations. That spectrum is associated with a certain temperature pressure profile in the atmosphere. And you make an initial guess about what the atmosphere is like and compute a spectrum from it. And in this case, it's just a black body. Normally you'd start with something a little more sophisticated. But you look at the difference between that spectrum and the observations. And you use that difference to refine your initial guess. You come up with a more complex model that is closer to the ground truth and compute a new spectrum from it. That'll get you a lot closer to the observations. You use the difference between the two spectra again to iterate on that. And eventually you wind up with a spectrum that matches the observations pretty well. And in theory should tell you pretty close to the true environment of the atmosphere. Now, I should note that it's a lot more complicated than this, a lot more iterations than this. In fact, we compute millions of spectra to try and fit the best one. And the way we do that is with a fancy computer code. So I've been working for several years on an atmosphere retrieval code called Apollo. It is a transit and emission spectrum Markov chain Monte Carlo retrieval code designed for flexibility of atmosphere models. It's designed to handle James Webb data, so it'll be good to go after launch this fall. And what I think is really the selling point is that it lets you compare different modeling paradigms for the atmospheres, which most retrieval codes don't get that deep into. So it doesn't just fit a model to the data, it lets you bring in a completely different model with a different chemistry code that you can plug into it, or a different analytic approximation to the temperature profile. And you can run different models and see which one gets the best fit. And there is a public beta of Apollo. Right now, you need your own molecular absorption cross-section tables to run it, but a version that you can use out of the box is in progress, and we hope to release that later this year. Apollo can compute model spectra. Here's some model spectra of transiting hot Jupiters that we created for the first Apollo paper. But the interesting part is that you can use it to retrieve atmospheric parameters of observations. And here's an object that we like to use as a benchmark for brown dwarf spectra. This is GJ570d. Might also see it listed as Gliese 570d. It's a type T8 brown dwarf, which means it's very cool, only 800 Kelvin. And at that temperature, we do not expect clouds, which keeps things simple. It's separated from its host star by 1500 AU. So we think it probably formed by direct collapse, and we expect it to have a low C/O ratio. And it should be pretty easy to measure because in this temperature regime, the spectrum will be dominated by water and methane. And these are the results. The black points are the observations. The blue line is our retrieved spectrum. So this is our best fit. And the red line is the difference between the two. It looks pretty messy, and there's always going to be a fair amount of noise involved. But these are also very low resolution data, not very many wavelength points, and it's not going to be quite as good a fit that way. However, it is competitive with what I think was certainly the industry standard at the time, is still pretty close to the industry standard. This is Mike Line et al. 2015 with Mike Line's Chimera code compared with my retrieval of the same spectrum with Apollo. And you can see the residuals are similar. It gets a similarly good fit. And we can find properties of the atmosphere. Here's the temperature pressure profile. So you can see from high altitude at 300 Kelvin down to the deep atmosphere at 300 atmospheres pressure, around 2200 Kelvin. We have molecular abundances, and these charts are always hard to read. I'm trying to figure out better ways to display it for the next paper, but short version is this is a probability distribution of different molecular abundances, and this particular square is water and methane. And the location and slope of this sort of broad line tells you the C/O ratio, and in this case, it's 1.15. Now, that's not what we expected. We expect a C/O ratio of about 0.5 because we expect it to be similar to its host star, which is similar to the sun. But it does match the results in Line et al. 2015, so it's at least consistent. And that's probably indicating some chemistry that we don't fully understand yet. Now, like I said, this is a low resolution spectrum. So the next step is to bring in new data. There are actually 4 data sets for GJ570D. This is the one you saw already from NASA's Infrared Telescope facility. Here's another spectrum at higher resolution from the United Kingdom Infrared Telescope. And you see it's a much better match over most of it. There's some weirdness going on here, and we think that's a calibration issue. There's always some uncertainty between the different wavelength bands. And when we account for that, we'll probably get an even better fit. This is from the Keck telescope in Hawaii. And this you can see is not such a good fit. We think this is also a calibration issue that we're investigating now, and could also be some variability. Even without clouds, brown dwarfs are variable, just like some stars are variable. And that could be affecting the results. And also from Keck, we have some near infrared and even into the optical. This goes up to 650 nanometers. And we can fit those wavelengths too. Apollo can fit warmer and more complicated objects as well. This is something I did last summer, kind of a side project. It's on the back burner for now, but we looked at some field brown dwarfs that are not stellar companions. This is a Keck spectrum, and we broke it down into individual bands to get a better fit. This is a T2 brown dwarf, which means it's considerably warmer, and it could have clouds, but doesn't appear to, since we did get such a good fit. And I like showing this because you can see very clearly these are potassium lines. Just like there are sodium and calcium lines in the sun spectrum, brown dwarfs have infrared potassium lines that the warmer ones do. And we're hoping those can give us better measurements of the surface gravity and mass of these brown dwarfs, because potassium lines are very sensitive to surface gravity. But like I said, that's kind of a back burner project right now. Right now, we're looking at stellar companions, and we have some Hubble Space Telescope data. This is from HN Pegasi b, which is another T2, but this one's a stellar companion. And stellar companions are important because they have known distances, and that gives us more accurate luminosities, more accurate radii, better mass estimates, and those can be used to do better retrievals and tell us more accurately what's going on in these atmospheres. So the next step on this project is to look at these directly imaged planets. This can be challenging. Most of the directly imaged planets are hotter L dwarfs, which definitely have clouds, but we have a sample of 6 T dwarfs, and I'm using the word planet broadly because it's really super Jupiters and brown dwarfs. Like I said, we use the same techniques to study them. But we want to look at these 6 objects, and there's maybe a dozen data sets between them. So there's plenty to work with. Measure the C to O ratios to try to figure out the distributions of the 2 populations, the direct collapse formation population and the core accretion formation population. And also my colleague Arthur Adams at Michigan is working on the L dwarfs. So before too long, we'll be able to add those in. We want to retrieve on James Webb data when it comes out next year. Eventually revisit transiting planets and other projects of opportunity. And of course, finish the official public release of Apollo. And to close, I just want to acknowledge the work of my colleagues, Michael Meyer, Fred Adams, and Arthur Adams at Michigan, and Mike McElwain and Avi Mandel here at Goddard. And with that, I will take questions.
Outstanding. There are a few this time in the chat. Anyone who would care to unmute microphone? Alex, why don't we start from you? You've got a couple in there.
Okay, I was just wondering, in addition to spectroscopy, is most of the, my mind is blown by how much information we've covered just in 1 hour that is known about exoplanets. In 30 years or a little more, that's amazing to me. So I wonder if the Hubble is also used to know most of what we know about exoplanets, or were other scopes used? And if you know that's true, which other scopes?
A lot of other scopes are used. Hubble only really has time to look at the most interesting planets, and getting a good statistical sample is important. So there are a lot that are observed by Keck, by Euclid, by another one, the Canada-France-Hawaii telescope is one. There's Gemini, Subaru, Magellan, all the large telescopes chip in this endeavor.
That's awesome. So another question I had was, how do you get your research to be included in the James Webb Telescope?
Well, you can submit.
That sounds amazing to me.
Yeah, well, you submit a proposal for telescope time, and we submitted a couple proposals related to this project. They unfortunately did not get selected, but also the James Webb Telescope data will be public. The calibration data and early release science will be public right away. And other projects, they're, I think it's called proprietary data, not in that it's a business, but people doing their own projects want the first crack at their data, but even that will be available after a year or two. So we can just crank through the public data with Apollo and get some good results.
Cool, thank you.
Very nice. Eric, you had a question?
Yeah, I was just thinking, going back to the early plot of the sizes of the planets, where you mapped out the SuperEarths and the hot and warm Jupiters. There didn't seem to be too many data points down below the SuperEarths. So we're getting to smaller things.
Right.
Yeah. So there's not as much, there's no cluster or anything. There's not much. Now, I'm wondering if some of that at least is that these are just harder to detect.
These are much harder to detect. Anything smaller than Earth, we don't have enough coverage, just don't have enough statistical ability to detect these planets to draw many conclusions about them.
So that's really not those dot. The absence of dots is not just there aren't planets there. It's just we don't know if there are.
Yeah, we don't know.
Okay, thank you.
Cool. Steve, you had a question?
Yeah, I was just wondering, you kind of made a note in passing that potassium lines are more affected by surface gravity. I was just curious if you could sort of expand on that, or why that is, maybe.
I don't know a lot about the physics of it. It's just that,
fair enough. It was just an
it's just
interesting
that
comment
potassium.
Yeah.
Potassium's a very strong absorber. And you can see there's these very deep troughs, and they're very sharp.
Mm-hmm.
And the width of those lines has to do with the temperature and pressure of the gas, and that ties in with the surface gravity.
Okay, thanks.
That's all that's listed in the chat. Does anyone else have questions for Alex?
Yeah, I do. I was trying to type mine in, but can you hear me?
Yeah.
Yes.
Yeah.
Okay, I don't show up, but you're referring to M dwarfs and L dwarfs. Are they types of brown dwarfs or planets?
They are. It's a little complicated. Short version is their types of brown dwarfs.
Okay,
Now, M dwarfs, they are both stellar spectral types.
right.
And M dwarfs are the coolest and smallest true stars, but they
Okay.
can also be young brown dwarfs. And L dwarfs are sort of middle-aged brown dwarfs. They're kind of middle of the pack. T dwarfs are the cooler brown dwarfs that are older or less massive. Now, the thing is, you can also plot giant planets like super Jupiters on the MLT spectrum.
Right. Okay, that cleared that up. Thank you.
I have a question.
question. Oh, go ahead, Scott.
Yeah, you referred earlier in the presentation, you were talking about, one of the slides had a list of planet detection methods, and there was one I wasn't familiar with. There was something about moderation. Wonder if you could explain what that for the. Oh, okay, yeah. Orbital brightness modulation.
I don't know what that is myself.
Okay. I guess we could Google it.
Fair enough.
All right.
I have a question.
Hmm.
And relation to atmospheric loss by planets like Venus. You mentioned ablation and dissociation. How about greenhouse warming? Is that
Well,
totally different topic, or?
that's a different topic. Greenhouse warming heats up the atmosphere, which can cause mass loss, but mostly for hydrogen atmospheres. And of course, Venus's atmosphere is mostly carbon dioxide.
Right. Okay.
Anything else? All right, all quiet. So Alex, that was marvelous. Thank you. Round of applause for everybody.
Yeah, that's right.
All right. Thank you so much. That was very good. And essentially that is completes the meeting for tonight, but we usually hang around for a little bit. If it was an in-person meeting, we would have a little hangout, a little get together at the talk and chat a little bit more with the speaker perhaps, and then afterwards go out to a diner. So we have to do all that just sitting in our rooms now. So essentially, feel free to hang out here and talk. And as long as you want to hold out, some of us will drop off gradually. But other than that, thank you very much, everyone, for showing up this evening. And we'll pass it over to Freeform now.
And thank you, Alex.
Let's stop the recording.
Jack.
Yes, sir.
I